current. No, this is 8.4. This is of the whole chapter. This is the key bit. This is the crux move. Because it pulls together lots of chapter 8, current and charge. So I is current. We know, billing, that the form for I is involving Q's and T's.
Q, delta Q over delta T.
Correct. So, we are interested in how fast those little electrons are drifting through the metal. We're just dealing with metals, alright? So we'll go for a wire, nice and straightforward. Beth, describe a wire to me using some scientific words.
Lattice structure, ions.
Keep going, it's good so far. Lattice structure of ions.
Surrounded by delocalized.
Awesome, with loads of delocalised or physically called free electrons, which zoom through in a straight line. Georgie?
We kind of wall around in the general direction, then that makes they collide with the ions in the lattice.
Good, so they're colliding with ions in lattice, so their motion is, what word would you use beginning with R, Holly? Random. So they have a random motion, but they do gradually move along in the direction of which terminal?
Negative.
These are electrons, good, in the direction of positive, and we say they something beginning with D, Abby. It's a key word. They amble along, random motion, but they are gradually moving one way. If you gradually move one way, beginning with D, no. Some of you are doing it in life. You drift through life in a random, haphazard way with some sort of general direction sort of imposed on your randomness. So it's called drift velocity. So in fact, there's the key words. Because you see all of those appear in the formula. So if you wanted to, you could jot those there, couldn't you? And then I can stand, take a deep breath, because it's the first time I've ever been filmed. A bit nervous. So on the right-hand board, we've got N's number density. N's number density, that doesn't mean much. That's not useful. Who's read the book? Number densities are much more useful. Zara?
It is the it's the concentration of, okay.
Yeah, that's encouragement.
Okay.
I'm not constipated, that's encouragement.
It's the number of electrons per cubic meter.
Yes, it's the number of electrons. Which type? The ones stuck in the ions or the ones free to move?
Free.
So it's the number of free electrons per cubic metre in the particular material that we're dealing with. And they call it number density, which you need to know. But actually, you need to think this. N equals number of free, I'm going to use free because it's less letters, number of free electrons per metre cubed. But it's called number density. There's the official list of what these little symbols mean on the right-hand board. Hiding, look. And we've got to get from that and those, we've got to get to here. We've got to show why that works. It's called deriving formulas, derivations. I don't know if you've ever done one, to be fair. I don't know if you've done one in maths or in physics. So let's start with a little picture, because a picture paints. Picture paints 1,000 words, that's a song. Might sing it for you one day. Picture paints 1,000 words. So there's our little bit of wire. What's this thing here, if I shade it? That's A, that's the cross-sectional area, isn't it? What are these little things? Good, they're the free electrons. So we could have a little key, that'd be nice. Dot equals free electron. What else have we got? Well, we need to know the drift velocity. Well, we don't need to know it, but it needs to appear on the diagram so it's in your brain. So the drift velocity, let's pretend these are all drifting that way with velocity v. Okay, remember that's just their average velocity in that direction, if you like, their average velocity, their average speed towards the positive terminal. Their actual speed at any one instant is changing all the time. Yvette, Why is their actual speed changing all the time? Because of what?
Because it will attract some protons and go to the outside charge.
I don't think so. There's a key little phrase, but that's fine. Just listen, see if someone else can get it. That sort of, think of the drift velocity as almost their average velocity. It's a little bit not perfect, but it is a thought in your brain. They are drifting along, but their instantaneous velocity at any one point, their velocity at any one point in time, is not likely to be v. You both answered similar number of questions, so I wonder if Phoebe can join in. Why is their actual velocity at any one instant in time likely to be different to v?
The actual velocity of the electrons.
Yes.
But I thought v was what defined the velocity.
V is their drift velocity. They're drifting through life in this general direction.
Constantly moving then.
Good, because their actual motion is random, because they're hitting.
Positive ion.
Good, because they're colliding with the positive ions in the lattice. So this is a sort of an average. Their average numbers of meters they're moving per second in that direction, in the direction that they're moving towards the positive terminal. And just to finish off, probably not particularly here, but it's good revision. What would that be, just as a bit of revision? If the electrons are moving that way,
Conventional.
conventional current. Conventional current. Because the electrons are negative and they're going that way, and the conventional current is always the way which sort of positive charges would move, if you like, positive to negative. Okay, so the derivation. We've got velocity v, we've got area A. The key of this is this picture. Current is rate of flow of charge. How much charge goes past any one given point per second. So I'm going to keep that end of this little bit of Wi-Fi. That's the point. I'm going to stand there counting how many coulombs of charge come past per second, because that's what current is. Current is coulombs per second. So from that one, I is coulombs per second. That's more useful for me. We all learn differently. I mean, you've got the form in the formula sheet, hopefully, but coulombs per second. So now, all we've got to do is work out how much charge is in that block, and then say, okay, it's going to move past that point, and all those free electrons will have moved past that point. Well, what would make it easy is if we said, okay, what number of electrons will move past that point in 1 second? And if we know the number of electrons that move past that point in 1 second, and we times it by E, that will give us how many coulombs move past that point in 1 second, which is current. So I'm going to set delta T equal to 1. So then it instantly gives me, if I can work out how much charge is past that point in 1 second, I have got the current. So, if delta T equals 1 second, then I need to know what length this little volume of wire would be. In other words, in 1 second, how far would that block have moved? Well, if it's travelling at v metres per second, guess what? If it's going at 10 metres per second, how far would these last electrons, if you like, right at the other end, how far would they have moved in 1 second if they were travelling at 10 metres per second? 10. If they were travelling at 1 metre per second, how far they go in 1 metre? 1. So in other words, in 1 second they travel v metres, don't they? So, if delta equals 1 second, then the electrons travel v metres. In other words, if we then think of this as one block, then that length there, if t equals 1 second, then this length, L, equals v metres. So we now can work out how many electrons are in there. Okay? So number of electrons travelling past point. I'm going to give this point a name. We'll call it point B. So that end is point B, just so we can refer to it. Number of electrons travelling past point B per second, remember, equals, well, we know that there's n electrons per unit volume, so all we've got to do is n times by the volume, and the volume is cross-sectional area times by L, agreed? You all know volume of a cylinder. So the number of electrons travelling past point B is n L. So what's the charge? Oh, but we know L is V. Yeah, we know L is V, don't we? So actually, it would make sense just to put NAV, because we want to obviously get our formula in terms of Anev. So that's the number of electrons travelling past point B per second, NAV. So how do we turn that into coulombs? Times it by E. Okay? Therefore, coulombs equals NAVE, and that's the amount of coulombs per second. Because we set the timer to 1 second right at the start, which is what enables us to set the length of this block of electrons. We set that equal to V because we chose 1 second. And so we got the coulombs per second. Well, guess what current is? So in other words, I equals, and then let's just swap the order so it's the same as the Bible. I equals A nav.